All right, so now we're going to take just a slightly deeper look at some of the different quantities you mentioned previously, and we'll take a look also at how they relate to some general units that you might be familiar with. So we mentioned before that temperature was one of the the things that was measured using one of the basic SI units. So just as a quick reminder, temperature can be thought of as a measure of how warm or how cold something is. And the temperature unit that we use a lot in science is the Kelvin temperature, which again is abbreviated uppercase K. Some of the other temperature units that you may be familiar with could be degrees Celsius. Okay, most of the planet uses that when they talk about weather, for example, and that's degrees C. And then we are familiar with things with degrees Fahrenheit and degrees F. There is no degrees Kelvin, by the way, it's just Kelvin, right? So we can convert between all these three different temperature units, um, going from, for example, Celsius to Kelvin is probably the easiest conversion that we'll do. So the relationship there is the Kelvin temperature is simply the degrees Celsius plus 273, right? If you have a temperature of 30 degrees Celsius, like in a warm summer day, you add 273 to it, you end up with 303 Kelvin. Now, if you do a little bit of math on it, what you'll also see is that we can determine the Kelvin temperature um, by rearranging this equation. We can also say, in fact, we can determine the Celsius temperature by saying a degree Celsius equal to Kelvin minus 273. Right, so you have a Kelvin temperature of 303. We simply take away 273, we end up with 80 degrees Celsius as the Celsius temperature. Now, similarly, we can go from Fahrenheit to Celsius. So, for example, again, something like 85 degrees Fahrenheit, typical summertime temperature. The relationship there that's used to convert to Celsius, Celsius is the Fahrenheit. You take away 32 and you divide that by 1.8. So you stick that in the calculator and you end up with approximately 29 degrees C. And that is roughly about where it should be in terms of how they're related to each other, right? So again, in terms of the conversions, not or the calculations, not the most complicated, but we will see temperature a lot. You'll be measuring temperatures a lot as well. So it's important to note whenever you make a measurement, right, you have to have the unit associated with it. Are we talking about Kelvin? Which, by the way, the Kelvin temperature is sometimes known as the thermodynamic temperature. We use that a lot in science, especially when we get the gases down the road. And there is a temperature below which we can't get lower than. So, for example, we maintain about the point absolute zero. So that corresponds to a temperature of 0 Kelvin. And that's a temperature beyond which everything stops, all motion, all molecular motion, all the motions within atoms and molecules and stuff. It's so cold that nothing even moves. So all motion stops at this. And if we were to convert this to, for example, Celsius temperature, right, then we take that Kelvin at this point here, we would subtract 0 Kelvin minus 273, and we end up with negative 273 Celsius. That is a super, super cold temperature. Even temperatures in outer space aren't that cold. They're maybe 4 or 5 Kelvin. But 0 Kelvin is the lower limit of temperature, right? That's absolute zero. Okay, let's take a look at length again. So we mentioned meter is the unit, the base unit that we use in the SI system. We also see derivations of that. So for example, we talked about centimeters or millimeters, kilometers, etc. And if you compare that to the imperial system or the British system, if you will, we have other units like foot, inches, yards, miles, etc. We talked about the relationship between those before. Now, if we take that length and we were to apply it now for the measurement of volume of different things, remember now volume, we define as the amount of space occupied by something. We can measure the dimensions if it's a solid. For example, this solid rectangular three-dimensional object here has dimensions of 1 centimeter wide by 1 centimeter deep by 1 centimeter high. If we calculate the volume of this, is simply 1 by 1 by 1, because 1 cubic centimeter, right? Which is also known as 1 cubic centimeter, or you've ever been to the doctor, for example, they sometimes refer to things in cc, not stands for cubic centimeter. So if you take the dimensions and we measure the dimensions of an object, we can calculate the volume. So whether it's, metric units, so in this case, we talk about cubic centimeters, we can also measure the dimensions in other units, inches, so we end up with cubic inches or cubic feet, for example. And we can convert, right? We talked about conversions before. We can convert from one to the other to get from the metric system to these other systems. When it comes to measuring the volumes of liquids, we can use slightly different units. So for example, we use the liter quite frequently, and liter has the abbreviation big L. Commonly in the lab, for instance, we use smaller volumes, so we use the milliliter. Again, in that 36 here, that means 1/1000th of a liter. So again, just a reminder, the relationship 1 liter here would be milliliters. And a very important relationship to note is that this volume of a liquid measured in mils is actually equivalent to a cubic centimeter. So 1 milliliter is the same as 1 cubic centimeter. So for example, if I have this cube up here of sides, all this, the edges being equal, 1 cubic centimeter, if I were to fill this with some liquid, water, for example, and then I measure the volume of that liquid, it would be 1 milliliter, right? In that cube. That's what this means. 1 cubic centimeter has the same volume as 1 milliliter. So you'll see those two units being used interchangeably quite frequently. Mass, which we said is a measure of the quantity of matter in an object, often used, or the units we often use are kilograms, which again means 1,000. That's a base unit in the SI system, but it does have a prefix in it. So 1 kilogram, and kilo meaning 1,000. Oops. So 1 kilogram would be 1,000 grams. Yeah, and then we have, all the other units that we're familiar with, things like pounds, ounces, etc., that we don't see a lot of in the science. Now, the thing to keep in mind with mass is that because it's the measure of the quantity of matter in something, the mass of something doesn't change. The amount of stuff in it does not change. However, we often use interchangeably weight when measuring mass. And weight is technically something different, right? Weight is a measure of the force of gravity on an object, and that can change, right? So if you think about, let's say a gold bar, okay, is going to have a certain mass. So the mass of the gold bar is the same on Earth, and it would have the same mass on the moon, for example. But if you measure the weight of that gold bar, right, the gravitational pull on that, it would have a higher or a larger weight on Earth compared to the moon. And the reason is the gravity is smaller on the moon, right? So the gravitational pull on it is less. If you see videos of people on the moon, for example, and take a step, they're kind of floating off into the air before they fall back down, and that's due to the gravitational force. So mass, the quantity of measure, the quantity of matter in something, that doesn't change. Weight, however, the gravitational pull on an object, that can change depending on where something is. Now, for all intents and purposes, right, if something is here on the surface of the planet, the mass and the weight essentially don't change a whole lot. They're kind of very similar to each other. So that's why we do use them interchangeably, but just keep in mind that they don't actually mean the same thing. So the next thing we can do is we can now combine a couple of these other units to make a new unit. So for instance, if we look at the ratio of a substance's mass to its volume. Okay, so again, mass, a measure of the amount of matter in something, and the volume, the space that it occupied. What we end up with something called that substance's density. Okay, and the density of something is, we can write that as an equation with the ratio of the mass to the volume, the mass divided by volume, and we can use those same units that we used previously. We can technically use any unit of mass divided by any unit of volume, but typically what we're going to see are units of, so usually we'll see grams over milliliters, which again means the same as grams over cubic centimeters, or sometimes we'll see kilograms per cubic meter, and then you also have the non-metric units, things like pounds per cubic foot, for instance. All of those are density units that we see. A couple of things to keep in mind with the way that we represent these units, for instance. And again, this is going to draw on your knowledge and go back to what we learned earlier in the semester, that's how we represent some of these relationships. That's the same as saying grams times milliliter to the -1. Right? Remember, anything to the -1 is 1 over that thing. And this little dot here means times. So this is the same. This is the same. Yeah? Similarly, grams per cubic centimeter can be written as grams centimeter to the -3. Okay, so you will see this in your textbook and other places. Don't get confused, right? That's what it actually means. And the thing about density also, because it's a ratio of a substance's mass to the volume, the density of something doesn't matter or doesn't depend on the size of the sample. Okay, so for example, you have a sample of aluminum. If you have 1 ton of aluminum, it would have a density of whatever it is, 2.7 grams per cubic centimeter. But if you have maybe half a gram of aluminum, it would also have the same density, 2.7 grams per cubic centimeter. And that is an indication of a property or a characteristic of density, which tells you that it is an intensive, or sometimes it's called an intrinsic characteristic. Okay, and what that means is this does not depend on the size of it, right? And that's in contrast to an extrinsic or extensive characteristic. This does depend on size. Sample. So for example, you have something like the volume. Okay, that's an extensive property or an extensive characteristic. Obviously, the more of something you have, the more volume it will occupy, more space it will occupy. Right? Mass is also an extensive characteristic or an extensive property. The more of something you have, the bigger the mass is going to be. Right? That's just intuitively correct. But the density, though, and the reason why it's intensive is that it is a ratio of the substance's mass to its volume. And we'll be making, or in lab, for example, we'll be doing a couple experiments that explore density in a little bit more detail. So if we can somehow determine the mass of our sample, determine the volume that it occupies, we can calculate the density fairly easily. And there are different techniques we can use to determine masses and volumes, which we will do in the lab. So as a quick comparison, if we compare densities, if we can, by doing a simple experiment, we can say, for instance, the relative densities of different substances by comparing them to one standard. So for example, if I have a container of water, so this is, and at normal temperatures and pressure that we're associated with, the density of water here is 1 gram per milliliter, or 1 gram per cubic centimeter. And if I were to place an object in this sample of water and observe what happens to it, I can make some deduction about the density of that particular sample. So for instance, if I put a piece of, let's say, iron in here, you can maybe guess what's going to happen, right? The iron is going to sink all the way to the bottom. Yeah, and if something sinks in water, that means that the density is greater than the density of water. We can say that the density of iron is more than 1 milliliter. Okay? And that's just based on the simple observation that we made. Similarly, if I put, let's say, a piece of wood on here, so let's say this is, I observe that the wood actually floats. Well, then what can I conclude? Well, then I can say that the density of the wood is less than the density of water, so it's going to be less than 1 gram per milliliter. Right, and that's the reason why, for instance, oil and water, oil doesn't sink, and that's because the density of oil, for instance, is less than the density of water. So we can make some very, very simple predictions just by doing some very simple, or making some simple observations as well. So let's take a look at a couple other of these different units. And again, we talked about time before. Seconds being the unit that's traditionally used, abbreviation lowercase s. Couple other units that we're going to see. So speed, for example, which is just a measure of the distance covered over the time taken to cover that distance. So usually in you'll see speed represented in meters per second. That's the first one here. Or kilometers per hour, looking at the speed of a car, or maybe the speed of wind, for example, or miles per hour, sometimes abbreviated mph. And speed is slightly different than something called velocity. Velocity is simply the speed in a particular direction, right? So you talk about the velocity of something, it's the speed in a given direction. So for example, we can say, the velocity of a car is 55 miles per hour, and then we'll say going in a northeast direction, right? Or the maybe the velocity of the wind, for example, if you're at a scene of a fire, for instance, and you have to record your observations, right? Where's the wind coming from? Maybe the wind contributed to the spread of the fire. Well, what was the velocity? You have to talk about the speed of the wind and also the direction as well, right? So those two go hand in hand. The other one that we see that kind of relates to time and movement is acceleration, right? And acceleration here is the rate of change of speed. And this the typical metric units for acceleration, we do meter per second squared, right? So it's saying how quickly is the speed changing per second. Yeah, you have an extra second here in the denominator compared to the regular speed. Sometimes you see kilometers per second squared. And then just to compare it to imperial units, you might see feet per second squared, or maybe even miles per second squared. So that's acceleration, the rate of change of speed. Let's take a look at a couple other units. We look here at force and pressure units, and these are some units that we're going to introduce now, but we're going to see a lot of them down the road, especially when we get to like gases and stuff. So let's define a couple things. So force, first of all, is just an interaction that results in a change in an object's motion. And the basic unit here that we use in the SI system is the Newton. It's abbreviated big N. And a Newton is a force that moves or that accelerates, would be a better term, mass of 1 kilogram at a rate of 1 meter per second squared. Right, so you can say that a Newton then 1 kilogram meter per second squared. And if we were to just do some conversions, the relationships between the foot and a meter, for example, we can show that a Newton is equal to about 0.224 force. Now, what another unit that kind of stems from force is something called pressure. And the pressure is simply defined as the force per unit area. And the SI unit for pressure is the Pascal. And this corresponds to units of 1 Newton per square. Right, so a force per unit per the unit area here is a meter squared, 1 meter by 1 meter. So in other words, if I were to apply that force on that area, that would be 1 Pascal that I'm applying to that particular area. There are a couple other pressure units that you may be more familiar with, which, for example, a bar is defined as 100,000 Pascal or 100 kilos, and the kilo is 1,000, sorry, 100 kilopascals. And then another unit that we'll see a lot of is atmospheres. Abbreviated ATM. This is not a metric unit per se, but we do see it a lot. So an atmosphere, 1 atmosphere of pressure is equal to 101.3 kilopascals. And this is what you're actually experiencing on a normal day. You experience this atmospheric pressure at sea level, for example. Okay, so elevation of 0 meters, you would experience that particular this pressure, 1 atmosphere of pressure. That's essentially is the pressure of the atmosphere above you. Pressing that with that force on the unit area. Another unit that you see is PSI, something that you may be way more familiar with than the other one. Just stands for pounds per square inch. So that's the P and the S and the I in that abbreviation. And just to give you an idea, 1 atmosphere of pressure, which is what you're being exposed to right now, that's about 14.7 PSI. 14.7 pounds per square inch. And if you think about how that compares to other amounts that you're familiar with, if you think about tire pressure, it's going to be about 40 PSI. That's about maybe 3 times the pressure of normal atmospheric pressure that we're being exposed to. So some of these pressure units you'll see more than others. But in terms of what we'll see in the metric system, Pascal, newtons per meter squared is the one that we'll see. All right, the last couple ones we'll take a look at here are energy units. And you can define energy, first of all, as the capacity for doing work. The unit that we're going to use in the SI system is the joule, J-O-U-L-E, which is abbreviated uppercase J. And that's the quantity of energy expended when applying a force. 1 joule would be the energy expended when applying a force of 1 newton through a distance of 1 meter. Right, that's the energy that we would expend to move that. Another unit of energy that you'll see and you may be more familiar with is the calorie. Okay, and that's used a lot in nutrition, for example, but there's a slightly different calorie unit that we'll see here. And this is defined as the energy needed to, and this is, now we're talking about thermal energy here, heat energy, if you will. So the calorie, 1 calorie, which is abbreviated CAL, is the amount of energy needed to heat 1 gram of water by 1 degree Celsius. So the amount of energy needed to raise the temperature of water, 1 gram of water by 1 degree Celsius is a calorie. And this will give you a relationship between calories and joules. So 1 calorie is the same as 4.184 joules. Right? For the nutritional calorie I mentioned before, that's actually has a slightly different notation. It's calorie with the uppercase C. So this is a calorie. So 1 cal there is actually equal to 1,000 regular calories. Okay, so 1 cal, nutritional calorie, is actually equal to a kilocal, regular calories, right? So when we look at nutrition labels, this is what we're actually seeing, calories with a big C, and that represents 1,000 of the regular calories. Okay, and then the last thing we'll take a look at here are the units of power. So power we can define as the rate at which energy is expended. Okay, so how much energy is used or needed per second or per unit time is what power is. And SI, power is expressed in minutes of watts. The abbreviated big W. And a lot of these units, by the way, as you can probably guess, they're named after people. Not all of them, but several of them are named after people. And watts is an example of this. So a watt is defined as 1. So 1 watt is defined as expending 1 joule of energy per second. Right, that's what a watt is. Because it's so small of a unit, sometimes we use preferentially kilowatt. Okay, W, for example, would be the abbreviation for that, and megawatts as well. You think about power plants and other things, that would be big M, big W. And if you think about also, you know, again, when you eventually get to this in your investigations and whatnot, we also use watts, kilowatts, megawatts, for example, to refer to the heat release rate or the rate of heat release from a fire that's often abbreviated or that often measured in kilowatts for megawatts. So for example, if you fill a wastebasket with paper, right, that can burn at a heat release rate of about 50 kilowatts, right? If you have a sofa that's upholstered, that can release approximately 5 megawatts when it's burning completely. So a lot of um, these units we're going to see, again, we're just introducing them right now, but you're going to use them, you're going to see them a lot in your future courses. Eventually you get into doing these types of investigations, you're going to have to record these and use the appropriate units